Alright, let's continue with our study of heaps. Not a whole lot left to talk about implementation-wise. So we have discovered the data structure, and we know that we can make it using just a vector. We can make a tree using a vector, which is the weirdest thing. We talked about the analysis of the insertion and the removal, which is the hardest part. And now it's time to package it all together nicely in what's known as the priority queue abstract data type. So we talked about the operations for those. You have push, where you just insert a new node into the heap with a given key. Then you have pop, peak is empty, and get length. Okay, so pop is a removal process, but it removes always the root, the maximal slash or minimal thing that's in your heap. And then peak just shows you that thing, gives you what's on the top without actually like removing it, and then is empty, checks for emptiness, and then get length checks for the size. So you can technically implement is empty by calling get length on yourself, maybe. So that's how we can talk about it. So push is super simple. Push is insert. Insert to the heap data structure. Kind of a waste of a slide, but that's all you need to do. Just insert into the data structure. You know how to do that. It's right there. Okay, insert into the heap data structure. Pop is just remove the top and remove the node in index 0. And you can implement this using the remove function, the remove process, or you can just like hard code the fact that, oh, it's always going to be the thing at the root that you're removing. Not too bad. So you're just removing the node at index 0, so you really swap it with the last node, pop the last node, dot dot dot. You know what to do from there. That's just the removal algorithm. Peak is go and look at the top. That's all you have to do. Return maybe a reference to it so you can maybe take a look at it, something like that, or maybe copy it because you don't want to change it. Things like that. Is empty, just check and see if the underlying vector is empty. Not too bad. And then size, like these are very short things after we talked about the implementation of the data structure. This is really all not too bad. And then size is just check, return the size, give back the size of the heap data structure, of the underlying vector. That stores all the nodes in the heap. So look at this implementation. Not too bad. So this is what you can do to a priority queue. It's essentially just a wrapper around the heap. That's all it is. Okay? So with that, I have a few more examples for you, and you might get out super early because of it. So the last thing that I need to teach you is, well, you've discovered it a bit on your own, but now that we know how to implement priority queues, how does C++ handle all this stuff? So let's take a look at the documentation. So believe it or not, in the queue header, not just is the normal queue, but is also the priority queue, so that's where we're going. And it takes a few template parameters. It's got the type of your underlying values inside of your heap, and then you give like what goes on inside that heap. You give the underlying representation. It's defaulted to a vector, and then you also give a compare, so that what function are you using when you need to go and compare your values. So that is all very interesting, and we're going to talk about these extra template parameters that we haven't talked about before. Like, everybody's got them. Like, Vector has some extra ones out here, but we don't talk about those. We're actually going to talk about all of these for the priority queue. Okay? So I think that's the first thing that I want to talk about. So let's make a new slide. So So it has 3 template parameters. The first is the normal one. The first is like your t. It's the underlying type of the values that you're storing. The second is the underlying representation of the heap. Defaults to a vector of that type. That's not all you have to use. It just needs to be anybody that has random access iterators. So if you click on this, you can learn more about what that means. I guess the other normal thing that we have is an array. You can use an array instead of a vector if you wanted to. Technically, I think you could also use a list as the underlying thing, because you can technically go to a certain index in a list, but it might be a bit harder than other things. Okay, so normally we're going to stick with the vector, though. That makes the most sense. Okay, then we have a comparison type. Okay, that one is a bit interesting. So if you read down here, it says more things. So it's a binary predicate that takes 2 elements of type t and as arguments and returns a bool. So it's going to make some object of this type and then call it with a function-like operator to compare those things. So it's taken a comparison class. And it tells us how to compare 2 t's, 2 things of whatever this type that we're putting inside our priority queue is. And that's important because we need to know how to compare these things for maximality, okay? Or minimality, whatever you want. Okay, so that's very, very important. By default, it is the less than operator. And so the comparison class called less t, which, let's talk about that after I write it down. So this is a comparison class that has its operator parentheses overloaded, implemented, to just return the result of, I don't know, it takes 2 parameters and then returns a less than b, if those are the 2 parameters. Let's call them a and b, and to just return the result of a is a less than b. So it's using the less than operator in a silly way. So that's all it's doing. This is our less comparison class. So it has this operator parentheses, and it takes 2 things of that type t, and it just figures out, hey, is one of those things less than the other? It returns the result of the less than operation. So it's really just a wrapper for the less than operator. So as long as you have that defined for your type, it's going to work. So the default for any type, as long as you've implemented operator less than for that type. So you just got to say, oh, what does it mean to be less than, for some object of your type to be less than another? Then suddenly you can have a heap. Suddenly you can sort things. Okay, so the last thing that I need to say is that it is going to be a max heap. The priority queue is hard-coded to be a max heap depending on its operation, okay? You can make it a min heap by changing the comparison. And this is a lot of words. This is making probably no sense at all right now, so I'm going to give you plenty of examples. Okay, so the first one that I want to show you is this thing called heap sort. It's beautiful. You can sort a vector, or anything, in fact. You can sort a list of elements using a priority queue. Okay, so that is the idea, and let's figure that out together. I guess the easiest way to do it is make a in reverse order sorting function. So the idea is we have some random vector, and we're somehow giving this to some function that we call heapsort. And it's given us back the vector of that thing sorted. How in the world does it do it? Oh, sorry, in reverse order. I'm getting ahead of myself. Let me just draw that instead. 5, 3, 1, negative 42. At least we're going to start out with it in reverse order. Can I just delete this? Yes, I can. Yay. Alright, so it's going to give us back that. Let's figure out how. So remember, what a priority queue does. I forced you to use it once back before you knew anything about it. Let's say we have a priority queue of ints. We'll call it PQ, and we'll do stuff to it. How do we insert something into our priority queue? We can say either push or in place. In place is a bit fancy. It's not really necessary. It calls the constructor is what it does. So we can focus on push right now. It'll copy it in there. Okay, so we'll say pq.push, I don't know, the things in this order. We can say 153, 17, negative 42. Okay, so now we've got everything inside of our priority queue. It'll order them with max priority things coming first. When we extract. So how do we extract values from a priority queue, you might ask? Well, all you have to do is say top. You can say top to access the top element, and then pop gets rid of the top element of this priority queue. So it's kind of like, it's half a queue syntax, half a stack syntax for C++'s implementation. It's like we're pushing to a priority queue, which adds something, and then we're popping to get rid of something. But then we're not saying front like we were with normal queues, we're saying top, which kind of makes reference to the top of a tree, like the root of it. So hopefully that makes sense. So those are our values. What we can do is extract them. Let's so while the priority queue is not empty, so the empty function figures out how big, whether or not it's empty. So while it's not empty, let's just keep on taking out a value. Keep on popping the priority queue. And if I could spell, there we go. As long as there's something in there. So we're going to look at the top. So int top equals pq dot top. Maybe we can call it like next element or something. And then we'll say pq.pop to get rid of it, because now we have it. So remove the max element from the priority queue, and then we'll say, we'll just print out the element for now. And then maybe a space. So what this is going to do is it's going to make a priority queue based on all these things, these numbers, and it's going to keep on popping it, taking things out. So we called insert a bunch of times on the stack, on the heap, sorry, and then we're going to keep removing the top element and getting it. So we're always going to keep getting the biggest priority thing. So the first thing that we popped, or the first thing that was on the top, was 17. And then once that's gone, the top is now 5, then 3, then 1, then negative 42. And that's beautiful, because that allows us to sort something. Like if we gave it these numbers, we could add all of these to maybe a vector. We could say sorted vec dot push back next element, and now suddenly we have a vector that we can use. Let's say for int x in sorted vec, we could output that x. So now we're building up a vector based on the sorted values that we had above here. Okay, so that's the idea. Maybe those values appeared in an original vector. So we can make a function based on all this, and we can call it heap sort. So this is heap sort. Okay, we're using a heap to sort something. We just keep on, just put everything into a priority queue, and keep popping it. That's all you need to do. You'll get everything out in order. Let's talk about the running time complexity of this, because that is very interesting. So, what are we doing? We are pushing n things. This is technically not what I'm about to say, but or maybe I should go through the entire thing. So to push n things onto a priority queue, well, the first thing is kind of free, right? It's constant to push the first one, because you just put it on the heap and there's nowhere else for it to go but the root. You don't have to move it around. But then the second time you add the 5, now you start to need to move it. Okay, so it's like it's always O of log of n, but the n is changing. Like it's log of 1, which is kind of constant, log of 2, it's on the order of log of 1 for the first insert, then log of 2 because it's now size 1 for the second insert, then log of 3. These are all base 2 logs, plus dot 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 up to log of n for the insertion, and this is bounded by like n times log of n, so that can be our idea. A quicker way to come up with this value is to say, oh, okay, this is hand wavy, I know, but I can explain this more in office hours if you'd like. It's O of log of n to push, and we're doing it n times. Technically n is changing because the size of the queue, the size of the priority queue is not n the first time we push, the second time we push, only the last time. But at the end of the day, it still comes out to O of n log of n times log base 2 of n in total to push. And and then you gotta pop them again. Again, you're saying n times a O of log base 2 of n kind of thing. Which becomes, again, O of n log base 2 of n to sort. And that's beautiful. So hopefully that argument made sense. I can be a bit more formal in office hours if you'd like, but this is the gist that I want you to get out of this. It's really not too bad to run heap sort, and we're going to talk about sorting later in this class. But oh man, does this blow a few out of the water. This is actually asymptotically optimal. You can actually do better than this for general purpose types. For ints, you can do slightly better than this. And maybe we'll talk about that when we get to it. So heap sort is a very nice application of a heap. It gives you, for most types in the universe, the fastest asymptotically fastest sorting method. There are other sorting methods that are also n log n that have a smaller constant factor, but asymptotically, this is as good as you get. It's beautiful. So that's heap sort. The next thing that I want to show you is how you change the max operation. So what if you wanted a min heap? So now we have to think about how the heap is using its operator. So how is it using that less t? I want my blue back, please. How is it using less t? It's using this to determine whether or not something is bigger than something else, right? Because it wants a max heap. So it's given A and B, and because it's a max heap, it's returning true. It's putting B above A. It's saying that B has a higher priority over A. When it's returning true when B is greater than A, so this is a less than operation, so it's A less than B. So it's not returning true when A is bigger, it's returning true when B is bigger, and that is how it determines. So it calls this function, if it returns true, then it's going to put B above A, not A above B. Hopefully that makes sense. It's using the less than operation, but it's using it like a greater than. It cares about this B. Okay, so C++ is using less of t. It's using the less than operator, like greater than, to determine whether or not something is bigger than something else. If you wanted it to do the opposite, you need to give it a function, and this is where it gets all weird in your mind, but hopefully with some examples it'll make sense. You need to give, as your comparison class, that returns true when the second argument is smaller than the first. That's how C++ is using this comparison class inside of priority queues. It's considering these two things. It wants to know whether or not the second one should come above the first one in the tree. Okay? And it's going to say that, oh yes, it must appear before it if this returns true. Okay? So whatever this function is, if it returns true, then it's going to put the second thing above the first thing. So B goes higher in the tree than A. And it's kind of backwards. It's using less than like greater than because it's implementing a max heap. So that's a lot of words. Let me just show you what this looks like in code. That means all you have to do is give the greater than. Okay? That's all you have to do. Just give greater than to make a min heap. Because then it'll be like, oh, should I put B above A? That's its question. Maybe I should write that over here. So C++, it's thinking. Should I put B above A? I know, I will call my comparison with A first, then B. If it's false, the answer is no. If it's true, the answer is yes. And the order of these parameters is important. Okay, that's all it's doing. That's all it's thinking. So that's why if you give the greater than sign as your comparison, be like, oh yes, is A greater than B? If that's true, I'm going to put B above A, and that's true and B is smaller than A. So we've just made a min heap. I'm sorry to confuse you like this. It's weird. C++ is weird. It was the wrong decision when they made this one. But let me show you how to do it. Okay, so let's make a priority queue. Well, let's just make a new file. I'll copy all this. Well, let's just make a priority queue like this, but not quite. We have to give more parameters now. Okay? So we got to fill them all in. We got to say, okay, well, the class is int. The container that we want to use is a vector of ints. We want the underlying heap to be a vector of ints. And to compare whether or not something should be above another thing, we don't want to use less anymore. We want to use, it's implemented for us, we can use greater. Okay? But let's implement it. Let's implement greater ourselves. You could technically do this, but I want to show you where it's coming from. So let's make a greater than comparison class. And we're going to give that. And all it needs to do is take two things. And it's an operator, parentheses, is how you use it. It returns a bool. It takes two things. Two ints in our case, because we're comparing ints. Int A, int B. And it needs to return true if B is smaller than A. So return A greater than B. Okay? So that's our priority queue. That's our comparison class that we're giving. And so now, we're actually going to get it in sorted order from smallest to biggest. Okay, so that's that. And hopefully it makes sense why this is working. It's using this comparison to determine whether or not the second parameter, the thing that it gives in the second parameter, should go above in the tree, the thing that is the first parameter. And so if we want a min heap, we'll make it B less than A. And then that'll prioritize smaller things. Okay? So now it's going to order the tree based on whether or not this returns true for small b's. Okay? Hopefully that makes sense. And then you can compare whatever you like now, as long as you give a certain kind of operation. And that is the final example that I want to give. So this requires a short segue on images. So just so that we're all on the same page, every picture that you store in your computer. It's made up of little tiny squares called pixels, right? Sorry if this is like something you are very familiar with. A pixel. It's just a square. And it has a color. It has a certain kind of color. So every pixel of an image has its color stored for it usually, depending on the kind of image, of course. The most common color type is RGB. It's a pair of three things: red, green, blue. Okay? I guess it's a triple of red, green, blue values. So it's like how much red, how much green is in this color, how much blue. And the values, so they're between 0 and 255, usually. That's what you get. So it's what's called an additive color type. And so 255 red, 255 green, 255 blue, like, is all the color. That makes white. And 000, none of any of those colors is black. Okay, so that's all you need to know for pixels and colors. That's RGB in a nutshell. So now I have made a very fun little program that uses a priority queue to fade an image to white, starting with the lightest pixels. So, I guess I should say lighter pixels have higher average RG values. That's all you need to know. So with that, I've made a fun little priority queue. That prioritizes lighter pixels and changes an image based on that. I'm going to change them all to white. Starting with the lightest ones. So again, this is a lot of words, I'm sorry. But let me show you an example. Dun dun dun. Here is this file, and I've made a folder inside of today's lecture files called fade, and it's got a few files that are automatically generated. The ones that I've made are helper.cpp, helper.h, and fade.cpp. Fade.cpp is where I'm going to show you. But here is a cute picture of my cat laying on my running shorts. So we're going to take this picture, and we're going to, starting at the lightest pixels, so probably along like the bottom of his body, like his belly, his arms and things. Those are going to be the first things to fade to white. And then it'll start with the carpet and like the highlights of these shirts and things. And then over here, like my laundry hamper is going to be one of the last things to fade to white because it's very dark. So we're going to prioritize the lighter pixels. We're going to fade those to white first, and we can use a priority queue. We can use a heap to do that. Okay, so let me go into the fade folder, and then I'll show you the implementation after I run it. So it's /fade, and then cat.png. And so here is it working. It's going to start at the lighter ones and start fading, and it gets the carpet. And it's still working over here because those are dark. So from lightest to darkest, it's going to fade the image to white. Okay? And that's the coolest example I can think of priority queues. Okay, let's go into this. This uses a very fancy library called Qt, and if you want to build this yourself, you'll have to install the Qt library with this terminal command: sudo apt install qt5 default. And then you have to generate a makefile using the qmake command, and then you can use the makefile by saying make, and it'll compile this. It's a big, long process, I'm sorry. This is a very ugly implementation as well, and I also apologize for that. It's just getting this done. So every pixel on an image has an RGB value, which I'm going to use ints to store those 0 through 255 values. Then also it has a coordinate, like the XY coordinates of this image. Like maybe this is, I don't know, it's like 0, 2, 3, right? Maybe 3, 2. That's a pixel at index 2, 3. They all have XY coordinates. So this is one pixel now. You know where it is, and you know its color. So I can compare pixels for lightness now by taking their average RGB values. Again, this is just a comparison on pixels. If I implement less than, the default operation for priority queues is going to work. Okay? And so this is, I want to prioritize lighter pixels, so I want to return true when B is lighter than A. And so I'll be like, oh, is lightness B greater than lightness A? And the rest of these are just ensuring that it's a total order on these things. If you're a math major, you'll understand. It's not too important, though. And then we get into this. This is the main operation, this fade function. What it does is it makes a priority queue of pixels. So it pushes each pixel from the image. You don't have to worry about how I'm doing, just that I'm doing it. So add every pixel from the image to this priority queue, and it's going to automatically order them based on, because I'm using the defaults, based on the less than operation. And so I made sure to define the less than operation in the way that I wanted to prioritize lighter things. And then I'm going to keep on popping off the brightest pixels and changing the current image. Okay? Based on that. And the rest of this is just to make sure that I don't try to like change one pixel at a time. That would like crash the computer because it takes too long. There's too many pixels for that. So I changed like a chunk of 1,000 pixels at a time. It's not a big deal though. And yeah, so we're using the priority queue to change pixel colors. That's all that I want you to get out of this. It's just an exciting little example. And so now you can see why it's prioritizing lighter pixels first, and then it's slowly fading because I'm using some I'm stopping the program for a second using this pause function to animate things. Okay, so hopefully that's a little fun example. You don't have to stare at this code too much. It's just using a priority queue to prioritize pixels. And with that, I think that's everything I have for you today. So not too much. Just trying to get you up to speed on how you might use priority queue yourself. So just remember those 3 things. Your t, you can always just give vector of that t again. And then your comparison, if you want to worry about it, it can do different things. For pixels, as well as just for numbers. You can make it a min heap instead of a max heap. And then the last thing that I want to say now is some exercises for you. Change my fancy example, because you're going to get the code. Change it to fade to black, starting with the darkest parts of the image. So do the opposite. So starting with the, change the less than operation to prioritize darker pixels, and then fade each pixel in order of priority to black instead of white, and so then it'll start in the opposite direction in the image that I gave, and you can use this with any image, of course. And then another fun example that you'll have to think about for a bit. I'd be happy to talk to you about this during office hours. It's a fun little concept. Try to think of a priority measure for integers that isn't max or min, isn't greater than or less than, that is. For max, it's less than, and for min, it's greater than for priority queues implementation. And create a priority queue based on that measure. So think about that. One fun one that I can think of off the top of my head is, here's your number line. Here's 0. How about you prioritize integers based on how close they are to 42? So here's your integer I over here. Like, how far away is it from 42? That's your priority. And fun things happen when you change this kind of priority. And it all still works. It's all still logarithmic time. It's all still fun. So yeah, I just want to leave you thinking on that. And I think that's everything. So now you're experts on heaps and you understand this entire comic. You're welcome.